Hello, Regents Chemistry fans! We didn't quite get through everything yesterday, so I thought I would start you off today, after you have finished your quiz, with the ending bit of the notes from yesterday. We got preempted with a fire drill, so here goes. This is at the top of the page. I'm not sure if this is page 8 in your notes. Take a look. This comes right after the heat of solution that I defined for you yesterday. So follow along. The heat of formation is the last type of enthalpy change, and this occurs when 1 mole of a substance is formed from its elements. So for instance, if you were to look up the heat of formation for aluminum oxide, if you look on table I, you should see an equation that looks something like 4Al plus 3O2 produces 2Al2O3. And then off to the side, Al2O3, and then off to the side in the right-hand column, you'll see the delta H, the enthalpy change, is negative 3351 kilojoules. Now those kilojoules, those 3,000 kilojoules, are for when you form aluminum oxide, but according to this reaction, this 3351 is per 2 moles of aluminum oxide. So if I really want the heat of formation, as this suggests, formation is formed from the elements in only 1 mole. So what I need to do is take this 3351 and divide by 2, because if I divide this by 2, I would divide this by 2, I would divide this by 2, and everything would be cut in half, including this number. So when you divide that, that's going to be, I don't know, negative 16,000 something kilojoules. Okay, so you have to be careful what the question is asking for. This one is asking for heat of formation. They might have just said, according to the equation, aluminum and oxygen make aluminum oxide. On table I, how many kilojoules of heat is released? And there you go, there's the 3351. We talked a little bit yesterday about energy being related to stability. So enthalpy and stability, if energy is released, then that means that you have more stable products, right? So if we look at this equation we were just talking about for aluminum oxide, is aluminum oxide more or less stable than its original elements? Well, a negative enthalpy change means that energy is lost. Energy is lost. That means it's exothermic, which means the products are more stable. The aluminum oxide that's formed is more stable than the original elements. Forming aluminum oxide, that's exothermic. You can tell that because of the negative sign on the enthalpy. And then a potential energy diagram. If we were to draw a potential energy diagram for the formation of aluminum oxide from its elements, here's time, here's potential energy. This is an awfully small diagram. Let's see, we can extend some lines up and kind of out like this. Whoops, if we were drawing straight, that would be good. But since it's exothermic, that means that when you start with these reactants and you end with these products, that means that there is a change in energy that goes from high to low. So once you have your reactants over here, this would be the aluminum and the oxygen, and that turning into product over here, aluminum oxide, Al2O3, you can see that they're of lower energy than the original product, the reactants, which means that that delta H, so that difference between where you end up, which is down here, versus where you started out, up here, that interval, that's the delta H. Now I don't have this labeled on the y-axis, but you could label it and you could subtract those values to find out the delta H. Okay, that about finishes the enthalpy and the heat of reaction using table I. But just to introduce the activity that you're now going to do in class on this Friday afternoon, I mentioned that some reactions are reversible. So by way of introducing this concept to you, I'm going to have you do this activity, but I need to give you this brief little intro. I think it'll help. Equilibrium is this idea that we actually have used throughout the year, but I've never really called it this. Equilibrium is this idea that a forward and a reverse reaction are occurring at the same time, but it's a special time when the rate or the speed of a reaction occurs in the forward direction at the same rate as it proceeds in reverse. Okay? So however fast the reaction is going forward, it's going in reverse at the same time, at the same rate. And so there's things that have to be true. It must be a closed system. We like to say a closed system means that there's no openings in the container, that gases cannot exit or enter, that you're not going to lose one of your products. It has to, of course, be a reversible reaction. When I think of burning something, like burning a marshmallow or burning a piece of paper, that's not really reversible because the products, the ash and the carbon dioxide that are lost, when I say lost, it's not a closed system, so they're not kept in a specific place and those gases escape and you can't put them back together. And it also must be a reaction where properties of the reactants or the products, the properties are measurable. And not only are they measurable, that they can be seen to get to some constant value, that they will stop changing. They might change, but then they stop changing. So I'm talking about things like color or concentration or temperature or pressure. These are all things that we can measure about a reaction, and they might change, but then they'll stop changing and we can determine a value for them. So reactions at equilibrium, we sometimes describe them as dynamic. If someone has a dynamic personality, that means that they have a sparkling, they have an energetic, they have a vibrant, there's something going on there. People want to be around dynamic people. So equilibrium reactions are ones where there's always something going on. That doesn't mean we can always see it. Maybe the particles are too small and we can't see them, but we see the effects of their movement, and then there might be an equilibrium reached. So it might be a little confusing. So let's do an activity, an equilibrium exploration of sorts that you're going to do now in class together. Find a partner and get the activity. Away you go.